Bismillah Rahman Rahim. In the name of Allah, the most kind, the most merciful. My name is Shahzad Ali, class MS, semester 2. Today my topic is scanning electron microscope. The main parts of scanning electron microscope are: the first part is source of electron, which is also called electron gun, column through which electron passes. This column have electromagnetic lenses, electron detectors, sample chamber, then computer and display to view the images. Computer and display are not a part of SEM, scanning electron microscope, but that are necessary to view the images. How scanning electron microscope works: electrons are produced at the top of the column by electron gun, accelerated down through the column, and pass through a combination of lenses and apertures to produce a focused beam of electron which hits the surface of the sample. The sample is mounted on a stage in the chamber area, and unless the microscope is designed to operate at low vacuum, both the column and the chamber are evacuated by a combination of pumps. The level of the vacuum will depend on the design of the microscope. That is a schematic diagram of electron microscope. Here different parts of electron microscopes are shown. The very top part is electron gun. It produces electron. These electron passes through different lenses. These are electromagnetic lenses. First lens is condenser lens. Then electron beam passes through spray aperture. Then second condenser lens. Then electron beam passes through deflection coil. Then final lens aperture, and then electron strike on the sample. The sample is mounted on the stage. The position of the electron beam on the sample is controlled by the scan coil situated above the objective lenses. These coils allow the beam to be scanned over the surface of the sample. This beam rastering or scanning, as the name of the microscope suggests, enable information about a defined area on the sample to be collected. As a result of the electron-sample interaction, a number of signals are produced. These signals are then detected by appropriate detectors. Sample electron interaction. The scanning electron microscope (SEM) produces images by scanning the sample with the high energy beam of electron produced by electron gun. As the electron interact with the sample, they produce secondary electron, backscat electron, and characteristic X-rays. These signals are collected by one or more detectors to form images which are then displayed on the computer screen. When the electron beam hits the surface of the sample, it penetrates the sample to a depth of a few microns. Depending on the accelerating voltage, mean how much voltage we apply, higher the voltage, higher the penetration, and the density of the sample. Denser the sample, less the penetration. Many signals like secondary electron and X-rays are produced as a result of this interaction due to sample inside the sample. Here is a schematic diagram of interaction between sample surface and beam of electron. At the top, electron beam which hits the sample and produce different type of electron. Primary electrons are electron produced by electron beam. These electrons hit the surface of the sample and produce scatter electron, which are secondary electron, then deep inside backscatter electron, then characteristic X-rays, then continuum X-rays and fluorescence X-rays. The maximum resolution obtained in a SEM depends on multiple factors like the electron spot size and interaction volume of the electron beam with the sample. While it cannot provide atomic resolution, some SEM can achieve resolution below 1 nanometer. Typically, modern full-size SEMs provide resolution between 1 to 20 nanometer, whereas desktop system can provide a resolution of 20 nanometer or more. When electron passed through a column, how their path is controlled. In light microscope, which is also called optical microscope, we use glass lenses to control the path of photons. But electron can't pass through a glass. The lenses that are used here are electromagnetic. They simply consist of coils of wires inside metal pieces. When current passes through the coils, a magnetic field is generated. And electrons are being charged particles are sensitive to magnetic field. Their path inside the microscope column can be controlled by these electromagnetic lenses simply by adjusting the current that is applied to them. Generally, two types of electromagnetic lenses are used. The first one, the condenser lenses. In the first lens, that electron meet as they travel through the sample toward the sample through column. This lens converges the beam before the electron beam cone open again and is converged once more by the objective lens before hitting the sample. So there are two lenses, condenser, which converge the electron beam, which make a cone when passes through the column. So it converges to a focus or specific point. Then beam sometime again open up in the form of cone, and that cone is again converged towards sample by objective lens. The condenser lens defines the size of the electron beam, which defines the resolution, while the main role of the objective lens is to focus the beam onto the sample. The scanning electron microscope lens system also contains the scanning coils, which are used to raster the beam onto the sample. In many cases, apertures are combined with the lenses in order to control the size of the beam. These main components of a typical SEM instrument are shown in following figure. In figure, at topmost, a yellow beam, which is electron source, passes through condenser lens and converges, passes through scan coil. Through scan coil it diverges, but objective lens again it converges toward the sample surface. Type of electrons. The interaction of electron with the sample can result in the generation of many different types of electron, photon, and other irradiations. In the case of SEM, the two types of electrons used for imaging are the backscatter electron, abbreviated as BSE, and the secondary electron SE. Backscatter electrons belong to the primary electron beam and are reflected back after elastic interaction between the beam and the sample. On the other hand, secondary electrons originate from the atom of the samples. They are a result of inelastic interaction between the electron beam and the sample. BSE comes from deeper regions of the sample. Following figure, while SE originate from surface region. Therefore, BSE and SE carry different type of information. Backscatter electron images show high sensitivity to difference in atomic number. The higher the atomic number, the brighter the material appear in the image. In diagram, electron coming from electron gun hit the sample. Near the surface, it produces secondary electron and deep the surface it produce backscatter electron, and very deep it produce X-rays. Secondary electron imaging can provide more detailed surface information, something you can see in following figure. In many microscopes, detection of the X-rays which are generated from the electron matter interaction is also widely used to perform elemental analysis of the sample. Every material produces X-ray that have a specific energy. X-rays are the material's fingerprint. So by detecting the energies of X-rays that come out of the sample with an unknown composition, it is possible to identify all the different elements that the sample contains. So there are two figures. Figure A produced by backscatter electron and figure B is produced by secondary electron, and the sample is ferric oxide. Mechanism of emission of secondary electron, backscatter electron and characteristic X-ray from atoms of the sample. In top figure, primary electron hit the valence electron and eject electron. Now electron are secondary electron which are ejected by outermost shell. In second figure, primary electron hit inside the shell and electron ejected are backscatter electron. These electrons are ejected from deep inside of atom of the sample. Sometimes primary electron hit the inner electron, ejected them, and empty space or is fulfilled occupied by outer electron. Outer electron when fill the empty space inside the shell, they release their energy in the form of X-rays. Electron diffraction techniques. Electron diffraction techniques can be divided by the energy used. It may be high or low, the geometry, transmission or reflection, and the type of beam, parallel or converging. So here are some terminologies and their abbreviation. ED is abbreviated as electron diffraction. HEED high energy electron diffraction. LEED low energy electron diffraction. THEED transmission high energy electron diffraction. Or HEED reflection high energy electron diffraction. Reflection high energy electron diffraction. SAED selected area electron diffraction. NED nano area electron diffraction. CBED convergent beam electron diffraction. LACBED large angle convergent beam electron diffraction. Here is a flow chart which relate different diffractions. Electron diffraction may be high or low with respect to energy. HEED LEED high energy electron diffraction or low energy electron diffraction. High energy electron diffraction have two types, transmission diffraction or reflection diffraction with respect to geometry. Transmission diffraction have further type diffraction. It may be parallel or convergent. SAED, NED, CBED, LACBED. Low energy electron diffraction. A beam of electron of a well-defined low energy, typically in the range of 20 to 200 electron volt, is incident normally on the sample. The diffracted electron can be observed by a fluorescent screen after energy filtering grids, which select only the electron with the same kinetic energy as the primary electron. Here, electron produced by electron gun having energy 20 to 200 electron volt strike the surface of the sample. Here is a crystal and diffracted and passes toward grid or screen. Reflection high energy electron diffraction. Electron having energy 5 to 100 kilo electron volt directed towards sample at very near QI 90, that is incident angle, keeps very long path length high energy electron in near surface region to increase surface sensitivity and also to have K component comparable with G of the crystal. Forward diffracted electrons strike phosphorus grid used to repel secondary and inelastically scattered electron. 50 kiloelectron electron have L is 0.055 angstrom and K is equal to 114 angstrom inverse. Electron diffraction pattern from single crystal. Single crystal consists of atoms arranged in an orderly lattice. Some type of crystal lattice are simple cubic, face centered cubic, abbreviated as FCC, and body centered cubic, abbreviated as BCC. In general, single crystal with different crystal structures will cleave into their own characteristic geometry. Crystals of quartz, calcite, or carbon, they all have different geometry. Single crystals are the most ordered of the three structures. An electron beam passing through a single crystal will produce a pattern of spots. From the diffraction spots, one can determine the type of crystal structure. It may be FCC, face-centered cubic, or body-centered cubic, and the latest parameter. The distance between adjacent planes, its value may be 100. Also, the orientation of the single crystal can be determined. Axis striking a single crystal will produce diffraction spots in a sphere around the crystal. Each diffraction spot corresponds to a single HKL. The distribution of diffraction spots is dependent on the crystal structure and the orientation of the crystal in the diffractometer. The diffracting condition is best illustrated with the evolved sphere in reciprocal space. So here is a diagram which show diffraction pattern. By that pattern, everyone can determine the structure, identify a crystal. Diffraction spots are sometimes called reflections. 3 cheers for sloppy terminology. From polycrystalline material. Polycrystalline materials are made up of many teeny single crystals. Most common metal materials, copper pipe, nickel coin, stainless steel forks, are polycrystalline. The single crystal grains in a polycrystal will have a random distribution of all the possible orientations. Ground up, powdered sample appear polycrystalline. A polycrystal is not as ordered as single crystal. An electron beam passing through a polycrystal will produce a diffraction pattern equivalent to that produced by a beam passing through series of single crystal of various orientation. The diffraction pattern will therefore look like a superposition of single crystal spot pattern, a series of concentric rings resulting from many spots very close together at various rotations around the center beam spots will produce. From the diffraction ring, one can also determine the type of crystal structure and the latest parameter. The orientation of a polycrystal cannot be determined. Polycrystalline materials are made up of tiny single crystals. Not ordered single crystal grain in a polycrystal have random distribution of all possible orientation. Diffraction pattern will therefore look like superposition of single crystal spot pattern. A series of concentric rings resulting from many spots very close together at various rotation around the center spot. From the diffraction rings type of crystal structure and latest parameter can be determined. One cannot determine the orientation of a polycrystal since there is no single orientation and flipping or turning the polycrystal will yield the same ring pattern. Thank you, student.